Hey everybody, we're going to do discussion C-2, nuclear fission and fusion. We're going to talk all things nuclear chemistry. Alright, so let's first talk about fusion. Nuclear fusion is the combination of small, light nuclei into bigger, heavier nuclei. So when we talk about chemical reactions, we're just talking about moving electrons around. But in nuclear, we're talking about combining the nuclei, so making new elements. Alright, so hydrogen, we're going to fuse hydrogen atoms into helium. Alright, so this reaction releases an enormous amount of energy, and it does not produce any nuclear waste. But it does take a lot of energy to initiate the reaction. An example is a hydrogen bomb. Now in the hydrogen bomb, hydrogen is being fused into helium, and that's what's releasing the energy. But it takes so much energy to initiate that reaction that they actually have to use an atomic bomb as the fuse. So they light off an atomic bomb, and that gives enough energy to start the hydrogen bomb going. Okay, so all stars produce their energy from nuclear fusion, and small nuclei are being converted to larger ones in stars, and that's where all the energy we feel as light and heat comes from. Now, as a fuel source, nuclear fusion would be amazing because it has a great energy quality, tons of energy per mass and volume, and it produces zero waste. But it's difficult for us to do here, actually currently impossible, because we don't know any materials that can contain the heat of the reaction. But this is something that scientists are working on, and if we can solve this riddle, then all the world's energy problems will cease to exist. Alright, so mass defect. In the sun, hydrogen are being combined to form deuterium. Alright, and that will further combine to form helium. Now a helium nucleus, as we know, is 2 protons and 2 neutrons, but the actual mass of the helium nucleus is slightly less than the mass of 2 protons and 2 neutrons. So when we do this fusion reaction, we are not conserving mass. But fear not, we are not violating any of the laws of physics because energy is conserved, and energy and mass are different forms of the same thing. So that difference in mass is known as the mass defect. Now that mass has been transformed into pure energy during the reaction, and we can quantify the amount of energy by using Einstein's famous equation E equals mc squared. In this equation, E is the energy released in joules, M is the mass in kilograms, and C is the speed of light, which is 3 times 10 to the 8th meters per second. We're going to go ahead and square that. So what that means is that a very, very small amount of mass, because it's multiplied by that big number, equals a huge amount of energy, and that's where the energy comes from. Alright, so here's an example of a problem they're going to give you with mass defect. They're actually going to want you to calculate the energy released during a fusion reaction. So it says a proton has a rest mass of that, and a neutron has a rest mass of that. A helium nucleus has a rest mass of this. Use this data to calculate the energy liberated during the formation via nuclear fusion of one helium nucleus. So basically it gives us the masses of all the particles and the mass of helium. So we just have to compare the difference between all those masses to find out what the difference in mass is. So the first thing we're going to do is calculate the mass defect. We'll add the mass of 2 protons and 2 neutrons and subtract the mass of the helium nucleus. So we're going to take 2 times the mass of each of those, subtract it from the helium nucleus, and we get the difference in mass is 5.03280 times 10 to the negative 29th kilograms, a very, very small mass. Alright, so the second step will be to plug it into E equals mc squared. So we're going to take our mass defect, multiply it by the speed of light squared, and we get 4.5 times 10 to the negative 12 joules. Now this might not seem like a lot of energy, and indeed it's not, but that is the amount of energy liberated per atom. And so if we were to scale this up to, a lot more than one atom, imagine multiplying that number by 6.02 times 10 to the 23rd. That would just be for 4 grams of helium. Alright, now we don't use joules at the atomic scale. We use a unit called the electron volt, and it is a lowercase e with a capital V. An electron volt, this is the definition. It's the amount of energy required to move one electron through a predefined electric field. So the conversion from electron volts to joules is this right here. So if we convert that amount of energy, we get that it is 2.8 times 10 to the 6 electron volts, or 28 mega electron volts. And that is how much energy is released by the fusion to create one helium nucleus. So binding energy. Binding energy is the amount of energy needed to separate a nucleus into its individual nucleons. Now, the higher the binding energy per nucleon, the more stable the isotope will be, because the harder it will be to remove subatomic particles from it. So iron, as it turns out, has the highest binding energy per nucleon, and so it's very, very hard to add to the iron nucleus or to take away from it. So here is a graph that shows all of the binding energies for all the elements on the periodic table. As you can see, iron, right up here, has the highest binding energy per nucleon of any other element. So elements that are smaller than iron will combine in order to increase their binding energy per nucleon, and those are the fusion reactions. And any element that is larger than iron would need to split and become smaller in order to become more stable. So you've often heard, probably if you're into stellar evolution, about how stars will continue to fuse new elements until you get to iron, and once you get to iron, all the fusion stops and the stars either collapse or explode or make neutron stars or whatever. Alright, so the hydrogen fusion equation. So you remember from Chem 1, we can represent what's happening in a nuclear reaction with a nuclear equation. So in the fusion of hydrogen, we're just going to have the isotope of hydrogen with 1 neutron and the isotope of hydrogen with 2 neutrons to produce helium and spit out another neutron. So this isotope we know is called deuterium, and this isotope is called tritium. So deuterium plus tritium makes helium and a neutron. Alright, so nuclear fission. Now, unlike nuclear fusion, which is the combination of small atoms, nuclear fission is the splitting of very large atoms. So anything that is heavier than uranium can undergo nuclear fission, which will form 2 smaller atoms. And if you add up the binding energies of the 2 smaller atoms, it'll be greater than that of uranium, so the overall stability increases. So this is an energetically favorable process. So controlled nuclear fission, this is what goes on in nuclear power plants. Alright, so this is an example of what is actually happening in a power plant. Take the isotope of uranium, uranium-235, and bombard it with neutrons. When they bombard it with neutrons, it will split apart and form 2 isotopes, in this case barium-141 and krypton-92. Now when this happens, 3 additional neutrons are liberated. Right? So that means those neutrons can then strike other uranium-235 atoms, which will split and spit out more neutrons, which will hit more uranium-235, which will split and spit out more neutrons, and then what you have is a chain reaction, and that is how a nuclear reaction occurs. So this is a kind of a crude drawing because it does not show the 3 neutrons coming from the uranium atom, but that's okay. We initially bombard our uranium-235 atom with a neutron. It will fizz and split and spit out more neutrons, which hit other uranium atoms, and you can see how this goes, and then you get kablamo, your nuclear explosion. Alright, so control rods and critical mass. Control rods are devices that are inserted into a nuclear reactor, and their main purpose is to absorb neutrons. Alright, this is how, in a nuclear reaction, they keep that nuclear reaction from getting out of control. Now, they're often made from boron, but sometimes you'll see control rods that are made of silver, cadmium, or indium. Now, the term critical mass, when I was a kid, I thought that critical mass meant that meltdown was imminent. But that it actually means that it actually refers to the exact right amount of material that will make a nuclear reaction sustainable in a nuclear reaction. So if the number of neutrons produced generation to generation stays the same, the reactor is known as critical. If the number of neutrons grows generation to generation, the reactor is called supercritical, and then they'll insert control rods to prevent a meltdown of the reactor. If there are fewer neutrons produced in successive generations, the reactor will be subcritical, and if they don't remove control rods, the reaction will fizzle out. All right, and finally, breeder reactors are nuclear reactors that create more fissile material than they use. And they use plutonium-239 as the fuel. Now, it's created by the neutron capture of uranium-238. And this is kind of important because uranium-238 cannot undergo fission, but plutonium-239 can. So by bombarding uranium-238 with neutrons, you can create fissile material. And the great thing, I mean, think about if you were driving your car and your car produced fuel as it drove. I mean, that's really what's happening here. So breeder reactors are really the wave of the future, excuse me. All right, so here's a problem with mass defect using fission. Now this is a little bit more complicated than the original example. It says, using the following data, calculate the energy liberated from the fission of 1 gram of uranium-235. So we know that uranium-235, when we did the fusion reaction, it was 1 nucleus of helium being formed. Now we're talking about 1 gram, which is a lot more than 1 nuclei. So we're going to have some additional steps here. So what we're given is a table of masses of all the particles that could be involved in this transition. As you will see, a proton is not involved. And we're given a conversion between atomic mass units and kilograms, because our table here is in atomic mass units, and you know that you have to use kilograms for E equals mc squared. So basically we're going to use the same procedure that we used before. We're going to look at the difference between the mass of the reactants and the products, calculate the mass defect, plug it in E equals mc squared, but then we're going to have a couple extra steps, as you will see. So let's go ahead and do this. Okay, so first thing we're going to need is an equation for what's occurring here. So we know in the nuclear reactor we are going to take neutrons and throw them at uranium-235. This is going to cause uranium-235 to undergo fission, and the two products we're told that will form are barium-144 and krypton-89. Now remember, we're also going to spit out 3 neutrons in this equation. So what I have to do is add up the mass of the reactants, subtract it from the mass of the products, and that will give us the mass defect. So let's go ahead and do that. Now before I start, what I'm going to do is cancel out this neutron and make that 2, because that way it'll make our math a little bit easier. So let's go ahead and add up the mass of all those products. So barium-144 is 143.922953 plus krypton-89, excuse me, which is 89.91959 plus 2 times the mass of a neutron, because we're going to have 2 neutrons on that product side. So 1.008665. Now we're going to subtract the mass of the reactant side, which is just the U-235. So uranium-235 is 235.04395. Alright, so let me pause this for a second to get my calculator. Hold on. Alright, so when I performed that calculation, I got that the change in mass, the mass defect, is 0.815923 AMUs. So now I'm going to need to convert over to kilograms for my mass defect, so I'm going to use that conversion factor. So I'll multiply this value by 1.66 times 10 to the negative 27th kilograms per AMU. And when I put that in my calculator, times 1.66 e negative 27, I get that my mass defect is 1.35 times 10 to the negative 27 kilograms. So one good piece of news here is that we can go down to 3 significant figures because we use that conversion, so we don't have to write all these huge numbers out anymore. So now we're going to plug that value into E equals mc squared, so 1.35 times 10 to the negative 27th times 3 times 10 to the 8th times 10 to the 8th squared times 3e8 squared squared. And that gives me 1.22 times 10 to the negative 10th joules. Now you're going to think you're done, but that is the amount of energy for the fission of one uranium-235 nucleus. So this is joules per atom. So now we got to go and figure out how many atoms of uranium we have. So I have 1 gram of uranium, 235. If I divide by the molar mass, that'll give me the number of moles, which is 0.00426. Times that by Avogadro's number, and that gives us a total number of atoms of 2.56 times 10 to the 21st. So if I multiply my energy per atom by the number of atoms, that will give me the total energy. So that gives me 3.13 times 10 to the 11th joules, which is quite a bit of energy. Okay, moving right along. All right. So again, only uranium-235 can undergo fission. But a severe majority of the world's uranium is in the form of uranium-238. So the two isotopes are separated in a process known as enrichment. So there's two methods of enrichment, diffusion and centrifugation. Now in both processes, the first step is the conversion of uranium ore, which comes out of the ground as UO2, into uranium-6 fluoride. And they do this in the following way. The uranium ore is taken from the Earth's crust. It's reacted with hydrogen fluoride to produce UF4 and 2 moles of water. Then the UF4 is reacted with gaseous fluorine, and that creates UF6, which is in the gaseous form. Now, UF6 has an octahedral geometry, and so it's a nonpolar molecule, which makes it gaseous. Now, once it's gaseous, you can separate it with these two techniques. So in diffusion, the UF6 is passed through a diffusion membrane. Now, diffusion, you remember, is how quickly a gas will spread throughout an open space. Now, the lighter gas is lighter, so it will diffuse at a more rapid rate. So this is one way they can separate out those two gases. And in centrifugation, it's a multi-part process where we take the UF6 and place it in a centrifuge. Now, the heavier isotope will get moved to the outside of the centrifuge, so that is how they will separate out those two gases. However, they have to do this a lot because the ratio of 238 to 235 is so great that if you want to achieve a certain purity, you have to do it over and over and over again. All right, so Graham's law of effusion. All right, so Graham's law says that the ratio of diffusion of two different gases will be directly proportional to the square of the ratio of the molar masses of the different gases. So the general formula looks like this. The ratio of rate 1 over rate 2 is equal to the square root of the molar mass of compound 2 over the molar mass of compound 1. So specifically for uranium, if I want to find the rate of effusion of uranium-235 versus the rate of effusion of uranium-238, all I have to do is take the square root of the ratio of their molar masses, and that will give me my answer. Very easy. This equation also is in the data booklet. So as long as you know what you're doing, those should be free marks. And we see that the difference, the ratio of the rates of diffusion is 1.006. That's very, very close to 1. And that explains why we have to centrifugate the UF6 so many times to separate out the two isotopes, because there's really not that much difference in the way they move. Okay, so next we're going to talk about radioactive decay. And if you recall from Chem 1, radioisotopes, which are unstable isotopes, will spontaneously decay and spit out a variety of particles in order to gain stability. So there's a number of different particles that can be emitted during radioactive decay, and here they are. First, because I'm using the document camera, I'm going to go through and talk about some of their properties, and then I'll give you the symbols. So alpha particles are helium nuclei. Now, because those are relatively big in terms of radiation, they can get stopped relatively easy, and they can get stopped only by traveling in air. So they're really not too big of a deal for us unless we ingest them. Beta particles are fast-moving electrons. Now, if you're very close to a stream of beta radiation, you can get a skin burn, but again, they get stopped relatively quickly. Now, gamma radiation is very, very high energy radiation, and that can penetrate very, very well. Anything. Really, it's only stopped by a few substances. One of them is lead. Neutrons, we know what those are. They're emitted during fission and fusion processes, as we saw. Now, neutrons, again, are rather big for radiation, and so they don't cause much damage to the outside of your body, but if you ingest something that's emitting neutrons, it can do some serious damage. A positron is the antiparticle of an electron. That means it's an electron with a positive charge, and we know that what protons are. They're the main fuel for fusion reactions, along with those neutrons. So let me go ahead and quickly give you the symbols for those. So an alpha particle is a helium nucleus, so we just show the symbol for helium. A beta particle is an electron, so we show a mass of 0 with a -1 and the letter E. Gamma radiation, the symbol looks like a diving fish. It's got a mass and atomic number of 0, so it looks like that. Neutrons have a mass of 1 but no atomic number, so we put a 1 for the mass, a 0 for the atomic number with a little n. Positrons, I'm just going to use POS here, those are everything the same as electrons, except for now the charge will be +1 because they're antiparticles. And finally, protons, people indicate with a mass of 1, atomic number 1, and an H, or you might see it as a lowercase p. You want to get in the video here? Stick your head on the camera, go for it. Say hi to everybody. You got to look up. Look up. There. There.
Hi, everybody.
All right, let me go back to my lesson. You little stinker. Okay, so again, radioactive decay is the process by which these unstable nuclei emit particles to become more stable. Right. Now, when they spit out these particles, especially the beta particles or protons, they actually turn into different elements. And that changing of one element into another is known as transmutation. So for you HL students, radioactive decay is a first-order process, and the half-life is related to what is known as the decay constant. And that follows this equation in Table 1, where the decay constant will be equal to the natural log of 2 divided by T1/2, which is a way of representing half-life. So transmutation, and radioactive decay can be quantified using those thermonuclear equations that we looked at before. So here's an example that you might see. It says write an equation for the transmutation by proton capture followed by alpha decay of protactinium-237. So it's really important to actually figure out what this problem is telling us. It's telling us that protactinium-237 is going to capture a proton. That means it's going to turn into a whole new element. And that element is going to undergo alpha decay, turning into a new element. So we're really going to have two different steps here. The first step, we're going to show that transmutation of protactinium-237 by proton capture, and then the radioactive decay of the isotope that forms, which is U-238. So let's go ahead and do that. So here we're going to have protactinium-237. I just got to get a periodic. Okay, so protactinium has an atomic number of 91. So that's going to go ahead and capture a proton. That's going to increase its mass number to 238, its atomic number to 92, and element 92 is uranium. Now that uranium-238 is going to undergo alpha decay, so it's going to split out an alpha particle and something else. So the something else must have a mass of 234 to conserve mass, and an atomic number of 90, and an element with an atomic number of 90 is thorium. So that's how you do that. That's pretty easy once you get the hang of it. All right, finally, half-life. Now the half-life is the amount of time it takes for exactly half of a radioactive isotope to decay into its daughter elements. Now, we can use two different equations to perform half-life calculations. The first is n equals n0 times e raised to the negative lambda t, and t1 half, which is the half-life, is equal to the natural log of 2 divided by lambda. Now remember, lambda is our decay constant. So these two equations are in the data booklet, so it's not really a problem having to memorize them, but you have to know what all of the factors in them mean. So n is the amount of isotope remaining after a time period. N0 is the amount of isotope that you started with. T is the time interval, and T1 half is the half-life. Now remember, lambda is the decay constant. Now for you HL kids, this is kind of like a rate constant. Half-life problems. It says the mass of a radioactive substance was measured and then remeasured 120 days later. So that gives us a time interval of 120 days. It was measured and remeasured, and they found that 56% of the original sample remained, deduced the half-life. All right, so it tells us that we have 56% remaining. That means we must have started with 100%, so our original amount will be 100, and our remaining amount will be 56. All right, so let's go ahead and do this problem. All right, so we have our two equations. Half-life equals the natural log of 2 divided by lambda, it's a weird lambda, and n equals n0 times e raised to the negative lambda t. So I'm asked to find the half-life. So if I have lambda, that will be a piece of cake, but I don't have lambda, so I'm going to have to use this equation to find it. Now, no zero there. In order to perform these calculations, you have to be able to work with natural logarithms. I'm not going to explain it here. So if you don't know what I do here, then just try to remember the overall form of what I do. So to isolate lambda, I'm going to take the natural log of both sides of the equation, which will give me the natural log of n, which equals the natural log of n0 minus lambda t. Now I'm going to isolate lambda, so I'll subtract natural log of n0 from both sides and divide by the time interval. I'm going to make that negative to get our lambda value. Now when we do that, and I already did this to save time, we get that lambda equals 0.00483. Now that we know that, calculating half-life is a snap. It's the natural log of 2 divided by 0.00483. I'm going to have to actually do that. All right. So the natural log of 2 divided by 0.00483, and that gives us 144 days. Now this answer makes sense because a half-life is 144 days. Since 120 days have elapsed, that is just under one half-life, and we have just over 50% of our isotope remaining. Piece of cake. All right, so the next example says a substance with a half-life of 8 hours. So I have my half-life as 8 hours. Notice I'm writing down my variables as I go. Has an activity of 450 units after 48 hours. So my time interval is 48 hours. And it wants to know the original amount. So 45 units must be my remaining amount. So let's go ahead and solve this one. Okay, so again we have our two equations. So half-life equals the natural log of 2 over lambda, and n equals n0 times e raised to the negative lambda t. So here we are asked to find the original amount, excuse me. So I have my equation here that contains the original amount, but once again I'm not given a value for lambda. If I can find lambda, I can solve for n0. So I'm going to use this equation up here to find lambda, since I know the half-life. So lambda will be equal to the natural log of 2 over the half-life. So that becomes a natural log of 2 over 8. And when we perform that calculation, we get our decay constant is 0.0866. Now that we know that, we can rearrange this equation to solve for n0. So I will divide both sides of the equation by e raised to the negative lambda t, and that will help us find n0. So n is 450 divided by e raised to the negative 0.0866 times the time interval, which is 48. And when we perform that calculation, we get 28,700 units to start with. Again, these are really not that difficult as long as you know how to rearrange the equation and you know what all the factors mean. Alright, finally, radioactive waste. So nuclear fission, whether it be in the form of an atomic bomb or a nuclear reactor, creates a lot of waste. And that waste has to be stored safely underground because it's very dangerous to living things. Now, radioactive waste will damage organisms by initiating chain reactions, and those chain reactions will create oxygen-free radicals in the body, or the superoxide ion. Now, those damage DNA because oxygen-free radicals will pull electrons off from anything that they come in contact with. And the products can also be used to make nuclear weapons, so they need to be stored effectively. All right, that is it for this discussion. Bring any questions you have to class and study and practice.